In the early years of the 20th century, science was racing forward at a breathtaking pace. Laboratories across Europe were buzzing with questions about the atom, the building blocks of matter, and whether the secrets of the universe might lie hidden inside its tiny core. In this world of rapid discovery, one woman stood quietly at the heart of it all. Her name was Lise Meitner, a brilliant physicist born in Vienna, whose sharp mind and relentless curiosity led her to uncover some of the most important truths of modern physics. Yet while her male colleagues would go on to receive the glory, she was left in the shadows of history, her contributions nearly erased. Her story is not just about science. It is about courage in the face of prejudice, determination in a world that told women they did not belong, and moral conviction when others surrendered to power. She worked side by side with Otto Hahn for more than 3 decades, only to watch him receive the Nobel Prize alone for the discovery they had shared. She fled Nazi Germany with little more than her dignity, yet carried with her the insight that would change the world forever. The understanding of nuclear fission, the process that would split the atom and unlock forces both creative and terrifying. This is not simply the tale of a forgotten scientist. It is the story of how history is written, of how bias can bury truth, and of how one woman's legacy still speaks to us today about perseverance, ethics, and the pursuit of knowledge. Welcome to Words of Time. In this video, we will uncover the remarkable life of Lise Meitner, the woman who helped split the atom, yet was denied the recognition she so deeply deserved. Lise Meitner's story begins in the heart of Vienna during the last decades of the 19th century, a city that was alive with ideas, discoveries, and debates. Vienna at the time was not only a political center of the Austro-Hungarian Empire, but also a place where culture, music, philosophy, and science thrived in parallel. Into this atmosphere, Lise was born in the year 1878, the third of 8 children in a well-educated and supportive Jewish family. Her father, Philip Meitner, was a lawyer who believed strongly in education, and unlike many men of his time, he thought his daughters deserved the same intellectual opportunities as his sons. Her mother, Hedwig, managed the household, but she too valued learning and encouraged curiosity in her children. From a young age, Lise showed a particular fascination with how things worked. While other children might have been satisfied to play with toys, she would often take things apart in order to understand their inner workings. Curiosity was not a passing childhood trait for her. It became the defining spark that carried her into the world of science. Growing up in Vienna meant she was surrounded by change. Scientific discoveries were reshaping how people thought about nature. In physics, the later part of the 19th century was filled with groundbreaking ideas. James Clerk Maxwell's electromagnetic theory had reshaped the understanding of light, and discoveries in thermodynamics were altering how scientists saw energy and heat. In medicine and chemistry, new techniques were improving life and challenging old beliefs. For a girl like Lise, hungry to learn, it was an environment that stirred ambition. Yet despite this environment, there was also the reality of social expectations. In Vienna, as in most parts of Europe, girls were not expected to study advanced subjects such as mathematics or physics. Instead, they were often prepared for domestic roles. Lise had to fight quietly but persistently against those expectations. In her early schooling, she showed herself to be a capable student, though opportunities were limited. Girls were often barred from higher levels of education. Lise finished the usual education available to girls, but that was not enough for her. She wanted to go further. At the age of 14, she realized that if she wanted to pursue science seriously, she needed to prepare for the university entrance examination, the Matura, which was usually taken only by boys. With the encouragement of her family, she undertook the challenge of preparing privately. This was not a simple task. She studied with tutors, taught herself languages, and delved into mathematics and physics, often spending long hours at her desk. It took determination and discipline, but she eventually passed the examination in 1901, making her eligible to attend university. This moment was an early triumph, one that marked her first step into the academic world that would define her life. When she entered the University of Vienna in 1901, she was already 23 years old, older than many of her male peers who had been able to begin immediately after school. She was determined, however, not to let the late start slow her down. The university at that time was still adjusting to the presence of women, since they had only been officially admitted a few years earlier. For many professors, Women in science were a novelty at best and a distraction at worst. Despite this atmosphere, Lise pursued her studies with passion. Physics drew her more than anything else. She was especially captivated by lectures from Ludwig Boltzmann, a giant in theoretical physics, known for his work on statistical mechanics. Boltzmann was a brilliant teacher, and he inspired her with his enthusiasm for understanding the hidden order of nature. His lectures were not just about formulas and experiments. They were about the beauty of natural laws. For Lise, this was confirmation that she had chosen the right path. The early years at university were not easy. The culture was steeped in male dominance. Most professors and students did not believe that women could contribute seriously to physics. Often, she was overlooked or treated as an outsider. There were times when she doubted herself, but her love for physics was greater than her fear of failure. She pushed through the isolation by immersing herself in study and by maintaining her sense of purpose. In 1906, after years of hard work, she completed her doctoral degree in physics, becoming only the second woman to earn a doctorate from the University of Vienna in physics. Her dissertation focused on heat conduction in inhomogeneous bodies, a topic that required a deep understanding of both mathematics and physical theory. The achievement was remarkable given the barriers she faced, and it gave her a sense of validation that she could truly belong in the world of science. With her doctorate in hand, she wanted to continue research. Vienna, however, had limited opportunities for women scientists. Many positions were closed to them. Encouraged by mentors and colleagues, she decided to look beyond Austria, and Berlin became the destination. At the time, Berlin was emerging as one of the most exciting centers of physics in Europe. Max Planck was there, and the city was alive with new ideas, including the beginnings of quantum theory. Yet even in Berlin, the doors were not fully open to women. At first, Lise was not officially allowed to attend lectures. She had to ask Max Planck personally for permission, and while he was initially skeptical, having said earlier that women were not suited for serious physics, he allowed her to sit in his classes. She quickly impressed him with her intellect and diligence, and over time he became one of her supporters. It was in Berlin that Lise encountered Otto Hahn, a chemist slightly younger than herself, who was working on the new and puzzling field of radioactivity. Radioactivity had been discovered only a few years earlier by Henri Becquerel, and it was further explored by Pierre and Marie Curie, whose groundbreaking work was redefining both physics and chemistry. Hahn was focused on the chemical aspects of radioactive substances, while Lise brought her background in physics. They met in 1907, and this partnership soon became one of the most important collaborations of her career. They complemented each other. Hahn was skilled in chemistry, able to separate and identify elements, while Lise had the physical insight needed to interpret the results. Together, they formed a productive team that would spend decades exploring the mysteries of radioactivity. Their early work was carried out under difficult conditions. As a woman, Lise was not given proper laboratory space at first. She had to work in a basement room without adequate facilities. Despite this, she persevered. She and Hahn conducted experiments on newly discovered radioactive elements, trying to understand their behavior and their transformations. The field was so new that every discovery felt like stepping into uncharted territory. They were essentially building a new science as they went. Their combined efforts led to the identification of several new isotopes and advanced the understanding of radioactive decay. The partnership was not only scientific, but also marked by mutual respect. Hahn recognized Lise's abilities, and despite the limitations imposed by the era, he valued her as an equal collaborator. Still, recognition from the broader scientific community was often skewed. While their joint work was widely acknowledged, it was Hahn's name that tended to receive more attention in official channels, reflecting the biases of the time. Lise, though frustrated, continued to dedicate herself to research, believing that the discoveries themselves were the most important reward. During these early years, radioactivity research was transforming science. It was reshaping the boundaries between physics and chemistry, forcing scientists to reconsider the stability of atoms, which had once been thought of as indivisible. Lise Meitner and Otto Hahn found themselves at the center of this revolution. They published extensively, contributed to the mapping of radioactive series, and built reputations as leading experts in the field. Yet for Lise, the journey was about more than recognition. It was about following the thread of curiosity that had guided her since childhood. She felt the wonder of discovering patterns in nature, and each experiment was, for her, a way of unlocking a new piece of the puzzle. By the 19-teens and 1920s, their partnership had become well established. They had weathered the disruptions of the First World War, during which both contributed to war-related work, though Lise tried to avoid direct involvement in military projects. After the war, they returned to their scientific pursuits with renewed energy. Their laboratory became a hub for young scientists eager to work at the forefront of nuclear research. Lise, though still facing the challenges of being a woman in a male-dominated field, began to be recognized more broadly as a physicist of great skill and insight. Her career during these decades reflected both her personal triumphs and the structural barriers she continued to face. Universities and research institutions often resisted giving her permanent positions or adequate pay. She had to fight for her place again and again. Yet she never let these obstacles stop her from doing science. Her dedication was unshakable, and her contributions helped lay the foundation for what would eventually become nuclear physics. By the middle of the 1920s and into the 1930s, Lise Meitner had established herself as one of the leading figures in the study of radioactivity. Alongside Otto Hahn, she had spent years mapping the behavior of radioactive isotopes, examining decay series, and probing the mysteries of atomic nuclei. Yet even as these scientific efforts advanced, she felt that the deepest questions about the atom were only just beginning to come into focus. For her, the atom was not merely a unit of chemistry. It was a gateway into the fundamental laws of nature. She often spoke about her work with a sense of awe, as if she were listening to nature whisper secrets, and her role was to interpret them with precision and care. By this time, nuclear physics had become a rapidly developing field. Discoveries were being made at an astonishing pace. James Chadwick's discovery of the neutron in 1932 opened entirely new possibilities for probing the atom, since neutrons, unlike charged particles, could penetrate nuclei without being deflected by electric forces. This discovery immediately suggested to many physicists that it might be possible to bombard nuclei with neutrons to induce transformations that had never before been observed. Lise was among the scientists who quickly grasped the importance of this. She saw that the neutron was a tool that could unlock secrets hidden at the very heart of matter. Her theoretical insights became increasingly important, complementing the chemical expertise of Hahn and others in the laboratory. The collaboration between Hahn and Meitner entered a new phase as they, together with the younger scientist Fritz Strussmann, began experiments bombarding uranium with neutrons. The idea was to see whether the nucleus of uranium, one of the heaviest known elements, could be pushed into creating new, heavier elements beyond uranium. This was a bold notion, for until then scientists believed that nuclei were stable against such radical disruption. The experiments produced puzzling results. Instead of the neat production of heavier elements, the chemical evidence sometimes suggested the presence of much lighter elements, such as barium. Hahn, being a chemist, hesitated to accept that uranium nuclei could be breaking apart in such a dramatic fashion. Lise, with her sharp physical intuition, began to see what might be happening. Her insight was to consider that the uranium nucleus could, under the impact of a neutron, elongate and split into two roughly equal fragments. This was a completely new concept, one that had not been proposed seriously before. To her, the splitting of the nucleus seemed to make sense of the confusing data. This idea later became known as nuclear fission. What set her apart was not just her willingness to entertain the idea, but her ability to connect the physics of the nucleus with the energy balances involved. She realized that if a nucleus as large as uranium were split into two smaller nuclei, the resulting pieces would be more stable, and the difference in binding energy would be released as an enormous amount of energy. It was a revolutionary insight, though at first she kept it close, refining her ideas before publishing. Yet while these discoveries unfolded, the world around her was darkening. In 1933, Adolf Hitler rose to power in Germany, and with the rise of Nazism came an increasingly hostile environment for Jews. Although Lise had converted to Protestantism years earlier, under Nazi racial laws her Jewish heritage was enough to make her a target. At first, she tried to continue her work quietly, believing that her position as a respected scientist might protect her. For a time, this seemed possible. She held a professorship at the Kaiser Wilhelm Institute, and her collaboration with Hahn continued. Hahn himself, though not Jewish, valued her contribution and tried to shield her from political pressures. But as the years passed, the laws and restrictions grew harsher. Jews were being dismissed from their positions, forbidden to hold public posts, and excluded from professional life. Each year that passed increased the danger she faced. By 1938, the situation had become critical. Austria had been annexed by Germany in the Anschluss, and as an Austrian citizen of Jewish heritage, Lise was now directly under Nazi rule. Friends and colleagues urged her to leave Germany, but she was reluctant. Her work meant everything to her, and she felt rooted in the laboratory where she had spent so many years. Moreover, leaving was not a simple matter. She had no official permit to emigrate, and securing one was nearly impossible by then. To stay was to risk arrest, yet to leave required a plan and help from others. She wrestled with the decision, torn between her dedication to science and her fear for her safety. The turning point came when it became clear that she could no longer remain in Germany without grave risk. With quiet determination, she began to plan her escape. The arrangement was made with the help of Dutch physicist Dirk Koster and others who sympathized with her plight. In July of 1938, she made her move. She traveled to the Dutch border, disguised as an ordinary passenger, carrying only what she could manage in a small suitcase. The crossing itself was tense. Had the border guards suspected who she was, she might have been arrested on the spot. But fortune favored her. She slipped across into the Netherlands, and from there eventually made her way to Sweden, where she found refuge. Her escape was harrowing and exhausting, but it saved her life. She later described those days as among the most difficult she had ever endured. In Sweden, she faced new challenges. She was safe from persecution, but she was also cut off from the laboratory resources she had relied on for decades. At first, she struggled to find a place where she could continue her research. The Swedish physics community was welcoming, but not as well equipped as Berlin, and her position was less secure than what she had known. Nevertheless, she was determined not to let exile end her scientific career. She threw herself into work with the same intensity that had always characterized her. The escape had been traumatic, but it also sharpened her sense of purpose. She was convinced that she had survived for a reason, and that reason was to continue her pursuit of knowledge. Meanwhile, in Berlin, Hahn and Strussmann pressed forward with the uranium experiments. Late in 1938, they obtained results that seemed undeniable. The chemical evidence pointed to the presence of barium, an element far lighter than uranium. This was astonishing. They themselves hesitated to interpret the results as nuclear splitting, but they sent word of their findings to Lise in Sweden. When she received the letter, she immediately began to think deeply about what it meant. Walking in the snow with her nephew Otto Frisch, who was also a physicist, she explained her interpretation. The uranium nucleus had indeed split into two smaller parts. She even calculated the energy release using Einstein's equation, showing that the process released energy far beyond that of ordinary chemical reactions. Together, she and Frisch coined the term fission, borrowing the biological word for cell division. Her theoretical explanation provided the missing key to the experimental puzzle. It was the moment when the mystery was solved. The atom could indeed be split, and the implications were immense. Nuclear fission would later become the basis of nuclear reactors and atomic weapons. Yet at that time, for Lise, it was primarily a scientific breakthrough. She marveled at the elegance of the process, at how the pieces of evidence finally fit together. Even in exile, deprived of her old laboratory and surrounded by uncertainty, she had made one of the most profound contributions to physics of the 20th century. Still, recognition was not equal. When the discovery was later honored, it was Otto Hahn who received the Nobel Prize in Chemistry in 1944 for his role in the discovery of fission. Lise was not included, despite her crucial theoretical interpretation. Many historians and scientists have since argued that this was a grave injustice, a reflection of both the biases against women and the disruptions caused by her exile. Lise herself was hurt but remained dignified. She continued her work and never sought revenge or bitterness. For her, science was a calling greater than personal accolades. As the 1940s unfolded, the world plunged into war. The discovery of fission quickly attracted the attention of governments, who realized its potential as a source of destructive power. In the United States, the Manhattan Project began, drawing on the talents of many physicists, including refugees from Europe. Lise, however, refused to take part in weapons development. She had fled from a regime that abused science for destruction, and she wanted no part in building weapons of unprecedented devastation. Her stance was firm. She would use her knowledge to understand nature, not to create tools of mass killing. Even when approached by colleagues who urged her to contribute, she declined. In this choice, she revealed not only her scientific brilliance, but also her moral compass. Exile did not silence her. In Sweden, she built a new life, continuing research into nuclear physics and mentoring younger scientists. She lectured, wrote papers, and contributed to the growing understanding of atomic nuclei. Her name gradually became recognized internationally, and she was invited to conferences and honored by societies that acknowledged her contributions. Though she had been denied the Nobel, she eventually received many other awards and tributes later in life, including being elected to the Royal Swedish Academy of Sciences and receiving the Max Planck Medal. Her reputation as a brilliant physicist and a person of integrity grew steadily. The years of exile had tested her, but they also showed the depth of her resilience. She had faced persecution, displacement, and professional marginalization, yet she never abandoned her devotion to science. Her story became one not only of discovery, but also of survival, courage, and ethical strength. She continued to remind people that science should serve humanity, not destroy it. When after the war, she learned of the atomic bombings of Hiroshima and Nagasaki, she was deeply saddened. She acknowledged that the chain of discoveries that began with her insights had led to this outcome, but she insisted that scientists had a responsibility to use knowledge wisely. For her, fission was a scientific marvel, not a weapon. Looking back on her life, one can see how her journey unfolded in stages. The spark of curiosity in Vienna, the struggle to establish herself as a woman in physics, the fruitful collaboration with Hahn, the groundbreaking insight into fission, the harrowing escape from Nazi Germany, and the continuation of her work in exile. Each stage revealed a different side of her character, her intelligence, perseverance, moral clarity, and humanity. She lived to see her contributions recognized, even if not always in the form she deserved, and she remained an inspiration to generations of scientists who came after her. By December of 1938, the tension of the times and the urgency of the research in Berlin intersected in a way that would change both science and the world forever. Lise Meitner had been living in Sweden for several months, having escaped Nazi Germany in a dramatic and perilous journey earlier that summer. Though she was safe, she remained emotionally and intellectually bound to her colleagues in Berlin, particularly Otto Hahn. Their friendship and scientific partnership had endured for over 30 years, and despite the political barriers and the looming war, they continued to correspond. Hahn, working with Fritz Strussmann, pressed ahead with neutron bombardment experiments on uranium, while Meitner, far away and stripped of her laboratory, relied on her sharp mind and her ability to interpret data from afar. In mid-December, Hahn wrote a long letter to Lise describing puzzling results. He and Strussmann had been bombarding uranium nuclei with neutrons, expecting to find heavier elements as products. Yet their chemical analyses stubbornly indicated something very different: the presence of barium, an element far lighter than uranium. Hahn admitted his confusion, and though he did not dare put it bluntly, he hinted at a suspicion that the uranium nucleus might have split. For a chemist, this was almost unthinkable. The nucleus had always been regarded as nearly unbreakable, except in small fragments like the emission of alpha particles. What Hahn was observing seemed to go far beyond established understanding. He turned to Meitner because he trusted her physical insight. Their correspondence was a continuation of a long habit, in which she supplied the theoretical framework for his experimental results. When Lise received the letter in Sweden, she felt its weight immediately. She was staying in Kungälv near Gothenburg, spending the Christmas holiday with family and her nephew Otto Frisch, who was also a physicist. The snow lay thick on the ground, the rivers frozen, and the air was sharp with winter cold. Yet her mind was ablaze with the possibilities hidden in Hahn's words. The thought that uranium might truly be splitting into two smaller nuclei was shocking, but not impossible. For years, she had wrestled with the question of nuclear stability and the forces at play inside the atom. Now, with Hahn's letter in hand, she sensed that the moment of truth had arrived. She and Frisch went for long walks in the snow, talking through the data. She sketched calculations in the margins of the letter, using the tools of physics that she had mastered since her student days in Vienna. Together, aunt and nephew reasoned through the puzzle. If uranium really was splitting into two lighter elements such as barium and krypton, the mass difference between the original uranium nucleus and the resulting products would translate into energy. Using Einstein's equation, energy equals mass times the speed of light squared, she quickly estimated the release. The result was staggering. The amount of energy liberated in a single fission event was far larger than anything seen in chemical reactions. It was the direct transformation of mass into energy, on a scale that until then had only been considered in stars. This realization was breathtaking. It explained Hahn's experimental results, it provided a coherent theoretical interpretation, and it marked a paradigm shift in physics. The nucleus, once thought of as nearly indestructible, could in fact be split by the capture of a single neutron. The process not only produced lighter elements, but also unleashed immense energy. The discovery of nuclear fission was now complete. Hahn had provided the experimental evidence, and Meitner and Frisch had supplied the theoretical explanation. In later years, Frisch recalled how excited they were on that snowy walk, aware that they were standing at the threshold of something revolutionary. Yet, even as she reached this breakthrough, Lise felt the bitter sting of her circumstances. She was in exile, stripped of her professorship and her laboratory, unable to perform experiments herself. She had to rely on letters and her nephew's companionship to continue her scientific work. The moment of triumph was shadowed by her exclusion from the immediate circle of publication. When Hahn and Stresemann prepared their paper announcing the chemical evidence of fission in January of 1939, they did so without including her name. They reported the barium results cautiously, presenting them as chemical findings rather than proclaiming the theoretical meaning outright. Lise's contribution, the physical interpretation that truly explained the process, was absent from that publication. This exclusion was painful. For decades, she had worked alongside Hahn, interpreting his results, shaping their shared research, and co-authoring countless papers. Now, at the most critical juncture of their partnership, her name was missing. Hahn justified this omission by arguing that, since she was no longer in Berlin and no longer directly involved in the laboratory work, the publication could not include her. Yet this reasoning ignored the reality of their collaboration, in which she had always provided the theoretical backbone. For Lise, the omission was another reminder of how easily women, and especially women in exile, could be sidelined. It was not just about recognition. It was about the loss of her rightful place in the history of discovery. To set the record straight, she and Otto Frisch quickly prepared their own paper, published shortly afterward, in which they outlined the theoretical framework of fission. They described how the uranium nucleus could elongate and divide into two nearly equal parts, releasing vast amounts of energy. This explanation, clear and elegant, completed the picture that Hahn and Stresemann had only tentatively presented. Their paper introduced the very term fission, borrowing from biology to describe the splitting of a nucleus in a way that was both descriptive and precise. From that moment, the word became part of the language of science. The world of physics responded with shock and excitement. News of fission spread rapidly across laboratories in Europe and America. For many scientists, the realization that such a process was possible immediately raised the question of whether a chain reaction could be achieved. If one fission event released neutrons that could trigger further fissions, the process might multiply exponentially, leading to an immense release of energy. This prospect carried both promise and danger. It suggested the possibility of new sources of power, but also the potential for unprecedented weapons. The implications were so vast that scientists everywhere recognized that the world had changed. For Lise, the discovery was deeply personal. She felt joy at having solved one of the great puzzles of nuclear physics, vindicating years of effort and insight. At the same time, she felt sorrow at being excluded from the central experimental paper and concern at how the discovery might be used. She had lived through persecution and war, and she feared that the new knowledge could be turned to destructive ends. Her conscience was clear. She would not work on weapons, no matter how compelling the scientific challenge. To her, the meaning of fission was not in bombs, but in understanding the hidden structures of matter. Her exclusion from the initial announcement has remained one of the most debated episodes in the history of science. Some argue that Hahn, under the pressure of Nazi Germany and the constraints of wartime publication, had little choice but to present the results quickly and in a limited way. Others see his decision as an act of erasure, one that reflected both the gender bias of the era and the betrayal of a partnership that had lasted decades. Whatever the reasons, the fact remained. Lise Meitner's theoretical brilliance had provided the explanation of nuclear fission, yet she was denied her share of recognition at the moment of discovery. In later years, when Hahn alone was awarded the Nobel Prize in Chemistry in 1944 for the discovery of fission, the injustice became even clearer. Many colleagues and historians pointed out that without Lise's interpretation, the discovery would have remained incomplete and perhaps misunderstood. She herself, though wounded, never allowed bitterness to define her. She continued her work, maintained her dignity, and became a symbol not only of scientific achievement but also of moral integrity. The Christmas letter of 1938 thus stands as one of the most important correspondences in scientific history. It captured the moment when experimental evidence and theoretical insight came together, bridging the gap between chemistry and physics and opening the nuclear age. For Lise Meitner, it was the culmination of a lifetime of curiosity and struggle, a moment of truth in which she saw more clearly than anyone else what was happening inside the atom. Though history often failed to give her the credit she deserved, the record of her role is undeniable. She was the mind that saw through the confusion to the heart of the matter, and the world has lived with the consequences ever since. By the closing years of the 1930s and the early years of the 1940s, the discovery of nuclear fission had already altered the landscape of science. The experiments in Berlin, the letter sent at Christmas, and the snowy walk in Sweden, where Lise Meitner and Otto Frisch calculated the enormous energy released by splitting the uranium nucleus, had marked a turning point in physics and chemistry. Yet the world that absorbed this knowledge was not the peaceful, cooperative community of science she had once dreamed of. War had overtaken Europe, persecution had forced her into exile, and the discoveries she had helped explain were quickly being drawn into military and political schemes that filled her with dread. For Lise, the years that followed were at once a vindication of her scientific brilliance and a bitter reminder of the injustices that could accompany it. When the Nobel Prize in Chemistry was awarded in 1944 to Otto Hahn for the discovery of nuclear fission, Lise was not included. By then, she was in Sweden, continuing her work under far more limited conditions, while Hahn was in Berlin, navigating the dangers of wartime Germany. The decision of the Nobel Committee shocked many who knew the history of the research. For 3 decades, Hahn and Meitner had worked together in close collaboration, publishing dozens of papers that combined his chemical mastery with her theoretical insight. At the decisive moment, it had been she who interpreted his puzzling data, she who applied Einstein's equation to reveal the release of energy, and she who, with her nephew, named the process fission. Yet the Nobel announcement recognized Hahn alone, as though the intellectual leap that completed the discovery had not existed. The reasons for her exclusion remain debated to this day. Some have suggested that wartime communication difficulties obscured her role, though her published paper with Frisch in early 1939 was widely read. Others point to entrenched gender bias, which made it easier to overlook a woman's contribution even when it was essential. Still others believe that the Nobel Committee simply chose to recognize chemistry alone, focusing on Hahn's experimental work, while ignoring the physics that Meitner had supplied. Whatever the explanation, the result was an injustice that wounded her deeply. Lise herself tried to maintain her dignity. She did not publicly campaign for recognition or attack Hahn directly, though in private letters she confided her disappointment and sadness. She had once believed that science was a meritocracy, where truth and discovery would be honored fairly. The Nobel snub taught her a harsher lesson about how recognition could be shaped by politics, prejudice, and circumstance. Even more painful was the direction that nuclear fission quickly took. Within months of its discovery, scientists in the United States, Britain, and other nations were already calculating the possibility of a chain reaction that could produce an explosive weapon. With the outbreak of war in 1939, the urgency of these projects grew. Many of Lise's colleagues, especially those who had fled Nazi persecution, joined what would become the Manhattan Project. They felt they had no choice. If Hitler's Germany were to build an atomic bomb first, the consequences would be catastrophic. But Lise resisted. She was invited to participate, but she refused firmly. To her, the use of her discovery to build weapons of mass destruction was unbearable. She had escaped the Nazis at great personal risk, and she could not reconcile the idea of turning the laws of nature into instruments of indiscriminate killing. "I will have nothing to do with a bomb," she said more than once, and she held to that decision even when it meant exclusion from the greatest scientific project of the era. Her refusal set her apart. She admired her colleagues and understood their fear, but she could not share their justification. In Sweden, She continued her research on nuclear processes and supported efforts to develop nuclear energy for peaceful purposes. She believed that fission could be a force for good if it were harnessed responsibly, providing a new source of energy that might one day ease humanity's dependence on fossil fuels. To her, the discovery was first and foremost a triumph of human understanding, not a pathway to destruction. When the atomic bombs were dropped on Hiroshima and Nagasaki in August of 1945, her reaction was one of sorrow. She grieved for the victims and lamented that science had been used to such ends. To colleagues who pressed her for her views, she replied with quiet conviction that science must serve life, not death. For many who knew her, this moral stance became as much a part of her legacy as her scientific work. She was not blind to the realities of war, nor naive about the power of fission. But she believed that a scientist had a duty not only to discover, but also to guide how discoveries were used. Her conscience remained clear because she had refused to participate in building weapons. In later decades, she supported international cooperation in nuclear research and spoke in favor of using atomic energy for medicine and power generation. She reminded young scientists that knowledge carried responsibility, and she embodied that principle in her own choices. In the years after the war, recognition of her contributions slowly began to grow, though always imperfectly. While Hahn's Nobel Prize remained a glaring omission, she received other honors. In the 1950s and 1960s, she was awarded the Max Planck Medal, became a member of several academies of sciences, and was celebrated as one of the great women in physics. She traveled, lectured, and continued to inspire. Yet she never fully recovered from the pain of being left out of the Nobel recognition. It was not a matter of vanity but of fairness, an acknowledgement of what she had truly given to science. To the end of her life, she remained modest, often deflecting praise, but those who spoke with her could sense the lingering wound. Her later years were also marked by reconciliation with colleagues. Though her relationship with Hahn had been strained by the Nobel episode, they maintained correspondence. Hahn himself, after the war, acknowledged her role more openly, though never in a way that fully corrected the omission. Others, including her nephew Otto Frisch and many physicists of the younger generation, were more vocal in insisting that her place in the discovery of fission should be recognized. For them, she was both a scientist and a symbol, a woman who had defied the odds, who had stood firm against injustice, and who had contributed to one of the greatest discoveries of the 20th century. When she died in 1968, she was remembered not only in Sweden but across Europe and America. Tributes poured in from scientists and students who admired her work and her character. On her grave in England, where she was buried beside her brother, the inscription chosen by her family read, "A physicist who never lost her humanity." Those words captured the essence of her life. She had sought truth in the structure of matter, but she had never forgotten compassion, conscience, and the human cost of discovery. In the decades that followed her death, the effort to reclaim her legacy grew stronger. Historians of science revisited the story of fission, scrutinizing the publications, the letters, and the recollections of those involved. Again and again, they found evidence of her central role. They showed how her interpretation had made sense of Hahn's experimental data, how her theoretical calculations had revealed the energy released, and how her intellectual courage had named and explained fission when others hesitated. Scholars and advocates argued that the Nobel Prize should have included her, and that its failure to do so was one of the most glaring oversights in the history of the award. Public recognition also expanded. Schools, laboratories, and institutes were named in her honor. Books and documentaries told her story, not only as a tale of discovery, but also as a reminder of the obstacles faced by women in science. In 1997, long after her death, Element 109 was officially named Meitnerium in recognition of her contributions. This rare honor ensured that her name would be permanently inscribed in the periodic table, a symbol of the respect she had earned. Though she had been denied the Nobel, the naming of an element was a profound acknowledgement that her place in scientific history could never again be overlooked. Today, when people reflect on the history of nuclear physics, her name is inseparable from the story of fission. She is remembered not only for her brilliance, but also for her perseverance in the face of exclusion, her courage in fleeing Nazi Germany, and her moral integrity in refusing to work on weapons. Her story serves as an inspiration for women who pursue science in fields still too often marked by inequality. It is also a reminder that discovery is not only about experiments and equations, but also about the character of those who make them. The Nobel snub, the atomic shadow, and the long struggle to reclaim her legacy together form the closing chapters of her life. They reveal the contradictions of a world where a woman could explain one of the greatest discoveries of the age and yet be denied formal recognition, where science could illuminate the heart of the atom and yet be turned toward mass destruction, and where truth could be temporarily obscured but not erased. Lise Meitner's life, in all its triumphs and trials, continues to stand as a testament to the pursuit of knowledge guided by conscience. The atom's secrets were revealed through her mind, but her heart never allowed her to forget the responsibility that came with such power. By the time the 20th century reached its closing decades, Lise Meitner's name was far better known than it had been during her lifetime. The struggle for proper recognition, the injustice of the Nobel omission, and the ethical choices she made in the face of war had become essential parts of her story. Yet what her life truly revealed went far beyond one discovery or one missed award. Her experiences illuminated a deeper pattern in science itself, a pattern of systemic bias, exclusion, and selective remembrance that shaped the stories people told about discovery. This, more than anything, is the lasting Meitner effect. The way her life forces us to confront how science, though devoted to truth, has often failed to tell the whole truth about who makes it. The Meitner effect lies first in the way her contributions were overshadowed by her male colleague. Otto Hahn, who worked side by side with her for more than 3 decades, was awarded the Nobel Prize in Chemistry for the discovery of nuclear fission, while she, who supplied the decisive theoretical interpretation, was ignored. Hahn himself knew the value of her work, and his private letters acknowledged her role. Yet in the public record, and in the judgment of the Nobel Committee, her part was erased. The reasons were not mysterious. She was a woman in a male-dominated discipline, an exile separated from her laboratory, and a physicist whose contributions crossed disciplinary lines that prize committees preferred to keep tidy. These factors combined to render her invisible at the very moment she should have been most visible. Her story reveals how recognition in science has never been purely about merit, but has been shaped by social structures, prejudices, and institutional blind spots. The second dimension of the Meitner effect is the way her exclusion was rationalized. Over time, justifications were offered. That she had not been in Berlin when the experiments were done, that her contribution was theoretical rather than chemical, that wartime circumstances complicated communication. Each explanation contained some truth, but together they amounted to a pattern of minimization that is familiar in the history of women in science. Their roles are often described as secondary, supportive, or interpretive rather than primary and creative. In Meitner's case, the fact that her insight transformed confusing data into a revolutionary discovery was downplayed in favor of the more tangible experimental record. This is a lesson in how historical narratives are built, how the lines between experiment and theory, between discovery and interpretation, are drawn in ways that privilege some kinds of work over others, often aligning with gendered expectations of who belongs at the center of the story. A third part of the Meitner effect lies in how her story was eventually recovered. Historians, journalists, and advocates for women in science revisited the evidence, combed through her letters, and reconstructed the path of the discovery. Their efforts brought to light the extent of her role and the injustice of her omission. This process itself shows that history is not fixed but contested. Who gets remembered and who is forgotten depends not only on what happened, but on who tells the story later. The recovery of her role demonstrates the importance of actively questioning official accounts and asking whose voices are missing. It shows that science, for all its devotion to objectivity, is still practiced by human beings embedded in societies with biases and hierarchies. To understand science fully, one must also understand these social dimensions. Yet the Meitner effect is not only about injustice. It is also about inspiration. Lise Meitner became a symbol for women who entered physics, chemistry, and engineering in the decades after her death. She showed that brilliance and perseverance could carry a woman into fields where she was not wanted and where she had to work harder than men simply to be accepted. She never used her struggles as an excuse to retreat. She pressed forward because she loved science too much to abandon it. Her modesty, her devotion to truth, and her refusal to compromise her ethical principles gave her a moral stature that resonated beyond the laboratory. Generations of women in science have looked to her as proof that they too can contribute at the highest levels, even if recognition is not immediately granted. Her life also provides a model of scientific integrity. At the moment when the discovery of fission was being absorbed into weapons programs, she drew a line. She could have joined the Manhattan Project, gained prestige, and played a role in one of the most consequential scientific efforts of the century. But she refused, not out of naivete, but out of conviction that science should serve humanity rather than destroy it. In doing so, she demonstrated that being a scientist is not only about curiosity and creativity, but also about conscience. This stance continues to inspire scientists who face ethical dilemmas in fields ranging from genetics to artificial intelligence. She reminds us that discoveries are not neutral, and that the choices scientists make about how to apply them are as important as the discoveries themselves. The impact of her life extends further still. By naming element 109 Meitnerium in her honor, the international scientific community ensured that her name would remain in the periodic table, where students around the world encounter it as part of the language of chemistry. This act of recognition, though symbolic, carries weight. It signals that the story of science must include those who were overlooked in their time. It encourages young people, especially young women, to see themselves reflected in the history of discovery. It says that even if the world once failed to honor her, the truth of her contributions can no longer be erased. Understanding Meitner's life is crucial for a complete and equitable view of scientific progress. Without her, the story of nuclear physics is distorted, reduced to half its truth. Without acknowledging the barriers she faced, one cannot grasp how much determination and resilience were required simply to practice science as a woman in early 20th century Europe. Without seeing the injustice she suffered, one cannot appreciate how recognition in science is shaped not only by discovery, but also by power. And without learning from her moral stance, one cannot fully reckon with the responsibilities that come with unlocking the forces of nature. Her life is not merely a case study in history, but a lens through which to examine how science works, how it fails, and how it might do better. In this sense, the Meitner effect is ongoing. It reminds us that for every well-known figure in the annals of science, there may be others whose contributions were obscured. It pushes us to ask, in every generation, whose names are missing from the record, whose work is being credited to others, whose insights are being dismissed because of gender, race, or background. It challenges us to build a culture of science that lives up to its ideals of fairness and objectivity, where recognition follows contribution without bias. It urges us to tell the stories of science not only as a series of breakthroughs, but as a human enterprise shaped by struggle, courage, and conscience. For young scientists today, Lise Meitner's story carries a message of perseverance and integrity. It says that the pursuit of knowledge is worthwhile even when obstacles loom, even when recognition is delayed, even when the world seems hostile. It says that the value of discovery lies not only in prizes or fame, but in the truth itself, and in the service of humanity. And it says that each scientist has a role in shaping not only the future of science, but also the moral framework within which science operates. As we reflect on her life from the vantage point of today, we see in Lise Meitner not only a physicist of rare insight, but also a person whose humanity guided her science. She grew up in Vienna at a time when opportunities for women were scarce. She carved a path into the heart of physics when few women were present. She collaborated in groundbreaking discoveries. She fled persecution with courage. She interpreted data that changed the world. She refused to turn science into destruction, and she endured injustice with dignity. Her legacy is not only in the concept of fission or the symbol MT on the periodic table. It is in the reminder that science, at its best, is a human endeavor that must be measured not only by what it discovers, but by how it honors truth, fairness, and responsibility. To study Lise Meitner's life is to see both the flaws and the potential of science. It is to recognize the biases that once erased her and to commit to a future where no one's contributions are overlooked. It is to understand that the power of discovery must always be balanced with conscience. And it is to be inspired by a woman who, despite being denied her rightful prize, gave the world a vision of what it means to be a scientist who never lost her humanity.